Okay, so length contraction equation. L is still the measured or contracted, but now it's length instead of time. L naught is still the proper value, this time for length. V is still the speed of the moving reference frame, and C is the speed of light. So same as before. So when I look at this problem, Mr. Borcherding wants to fit a 3-meter car into a 1-meter bike. So I have to ask myself, I have two lengths, so one is L, one is L naught. Which is the proper length? Which is the length measured by the observer in the reference frame? And which is measured by the observer outside the reference frame? And then V is the velocity of said reference frame. So the car is what's moving. So the car is my reference frame. So which length, 3 or 1, is going to be measured by a person in reference frame with the car? 3. A person standing next to the car, moving in reference frame with the car, will measure it to be 3 meters long. Someone on the outside is going to see it to be 1 meter long because they're going to see length contraction. So L is 1 meter, and we're solving for V. So when I set up the equation, I'm going to get this. L equals L naught times the square root of 1 minus V squared over C squared. Now, as your example, I wanted you to get one that's kind of a funky math one. I want to get you some practice with some funky math so that when you get to the problems, there's one that's a funky math problem, but then there'll also be some that will be a little bit more kind of normal to what you would expect. So we'll kind of look at that one. Those ones you can probably figure out. Did I lose my practice? Yeah, I'll figure it out. Anyway, so there's that. So let's go ahead and solve this. So I'm solving for V squared, so I need to divide both sides by 3 first. Okay, so that's 0.3. Now I need to get rid of the square root. I can't do anything else before I get rid of the square root. So I'm going to square both sides. And if you're going to need a calculator, again, make sure you trade something out to get one. Okay, so this is 0.11 repeating equals 1 minus V squared over C squared. Okay, we got to get V by itself. So I'm going to subtract 1 from both sides. So 1 is positive. It's doing adding and subtracting. So I'm going to subtract 1 because 1 is positive. Okay, that gives me negative 0.88 repeating. Let me go ahead and indicate that these are all repeatings. Equals negative V squared over C squared. Okay, we still need to get rid of this C because we got to get V by itself. So I'm going to multiply C squared to both sides. Okay, there go the C's. So negative 0.88C squared equals negative V squared. The negative we want to get rid of, so essentially you're going to divide both sides by negative 1, which the negatives just go away then. So 0.88C squared equals V squared. All that's left, square root both sides. Now, you might have been saying to yourself, Mr. V, why are we keeping this C squared around? This is just annoying. Why not get rid of it? Here's why. When I square root C squared, I get C. And when I square root 0.88, I get 0.94. So my answer is 0.94c. That's why I left the c alone. Notice I could have plugged in my value 3 times 10 to the 8th, but instead I left c alone. I just left c, left c, left c, left c, left c, left c, all the way until I get to the end when I screw both sides, and now I'm left with just 0.94c. So in other words, in order to have a 3-meter car fit in a 1-meter box, I had to travel at 94% the speed of light. Sweet. So there's your answer. Okay? Yes?
Isn't the speed of light infinite?
Huh?
Isn't the speed of light infinite?
No, it's not infinite, but it is the fastest you can go. But it is a set value. Yeah. If you go the speed of light, I suppose time might feel infinite. Because if you went the speed of light, essentially your time would be infinite compared to Earth's time. So don't think about it too much. All right. What I want you guys to do is 3 and 4. So 3, Sagittarius A, the black hole at the center of our galaxy, is about 26,000 light years away from Earth. If you flew a spaceship at 0.95c, what distance would you measure it to be that your spaceship is traveling? So this is the thing to think about. So if you're traveling at really high speeds, you are not going to measure the distance between objects to be the same. Okay, length contraction will happen. So you have to decide who is measuring this. Is this the proper length, or is this the measured length contracted length? Okay, so you have to decide that. And then number 4, a spaceship passes you at a speed of 0.6c. If the ship appears to be 7 meters long to an outside observer, how long would the pilot of the ship measure it to be? Okay. So these are both kind of back to the normal length contraction. The reason I showed you the example a little bit different, I wanted you to see an example where you solve for v. You should be able to solve for v. You will see a question like that come up every now and then. So go ahead and work on 3 and 4 on practice 2. I'll come around and see what questions you have. After a little while, I'll give you the answers to those 2 so you can check your work. And then I'll give you about 10 to 15 minutes or so to work, depending on how long it looks like people need. Then I'll stop you. We'll come back to note C, and we'll do number 3. Okay? So go ahead and work there, see what you guys can do. I'll come around and answer questions. Make sure you keep your phones put away, that kind of thing.